History of Neptune, the last guardian of the solar system. Here we are at the final stop of our extraordinary journey through the most extreme frontiers of the solar system. After exploring Uranus's magnetic anomalies and its upside-down rotation, we're heading toward the ultimate planetary frontier, Neptune, the eighth and most distant of the major planets. A world of titanic storms and profound mysteries that reigns supreme in the frigid cosmic periphery. This ice giant doesn't simply represent the final chapter of our exploration, but embodies the triumph of mathematics over chance. The first planet in history discovered not through direct observation, but through theoretical calculations. A world where winds reach supersonic speeds that defy all physical logic, where a great dark spot appears and disappears like an atmospheric phantom, and where a captured moon dances an orbital dance backwards, challenging gravitational conventions. Are you ready for this final epic journey to the edges of our planetary system? Neptune dominates the most remote regions of the solar system from an average distance of 4.5 billion kilometers, or 2.8 billion miles, or 30.1 astronomical units from the Sun. At this incredible distance, sunlight takes more than 4 hours to reach this frozen world, where illumination is 1,000 times weaker than what we experience on Earth. Yet, as we're about to see, despite this energy poverty, Neptune turns out to be the most dynamic and meteorologically active planet in the entire solar system. With a diameter of 49,528 kilometers or 30,775 miles, Neptune is slightly smaller than Uranus at 50,724 kilometers, but its higher density, 1.64 grams per cubic centimeter versus 1.27, gives it a mass equal to 17.5 times that of Earth compared to Uranus's at 14.5. Neptune's orbital period extends for 164.8 Earth years, a time so long that since its discovery in 1846, it has completed barely one complete revolution around the Sun in 2011. Rotation on its own axis takes 16 hours and 6 minutes, slightly faster than Uranus. Unlike its predecessor, Neptune's rotational axis has a normal inclination of 28.3 degrees, similar to Earth's, creating conventional seasons that last over 40 Earth years each. Despite receiving only 1,000th of the solar energy that reaches Earth, Neptune maintains atmospheric temperatures of minus 218 degrees Celsius or minus 360 degrees Fahrenheit, paradoxically warmer than those of Uranus despite being farther from the Sun. This thermal paradox is explained by the fact that Neptune radiates 2.6 times more energy than it receives from our star, testifying to an interior still active from geological and thermal standpoints. A planet found through celestial mechanics. The story of Neptune's discovery represents one of the most fascinating chapters in modern astronomy, demonstrating the predictive power of mathematics and theoretical physics. It all began with a supposed orbital anomaly. After Uranus's discovery in 1781, astronomers noticed that the planet didn't follow exactly the orbit predicted by Newton's laws. These orbital perturbations suggested the presence of another massive body gravitationally influencing Uranus's movement. In 1843, young English mathematician John Couch Adams, then a student at Cambridge, undertook the ambitious challenge of calculating the unknown planet's position based exclusively on the observed perturbations. His calculations, completed in 1845, identified a specific region of the sky where the mysterious eighth planet should be located. However, the British astronomical establishment showed little interest in Adams' predictions, not following up on his request for direct observations. Meanwhile, in France, astronomer Urbain Le Verrier was conducting independent calculations, arriving at surprisingly similar conclusions. Le Verrier managed to convince German astronomer Johann Galle at the Berlin Observatory to search for the planet in the predicted position. On the evening of September 23, 1846, Galle and his assistant Heinrich d'Arrest pointed their telescope toward the constellation Aquarius and, comparing observations with detailed star maps, identified an object that didn't appear on the charts, located less than 1 degree from the theoretically calculated position. This discovery sparked an international controversy over scientific priority, with the British and French claiming credit. Today, Adams and Leverrier are recognized as co-discoverers of Neptune, celebrating the triumph of the scientific method and international collaboration. The name Neptune, suggested by Leverrier himself in honor of the Roman god of the seas, was universally accepted, maintaining the mythological tradition in planetary nomenclature. Hey guys, just a moment before we continue. Be sure to join the Insane Curiosity channel and leave a thumbs up. Click on the bell, you'll help us to make products of even higher quality. Anatomy of an ice giant. Neptune's atmosphere, relatively thin compared to the planet's size, is composed of 83% molecular hydrogen, 15% helium, 1% methane, and traces of deuterated hydrogen, ethane, and water vapor. Like Uranus, it's the atmospheric methane that gives Neptune its characteristic deep blue coloration, absorbing red light and reflecting blue wavelengths. However, Neptune's blue appears more intense and vivid than that of Uranus, suggesting the presence of an additional component not yet identified that amplifies the selective light absorption. The atmosphere hosts the most extreme and dynamic meteorological phenomena in the solar system, a paradox considering its distance from the Sun and the consequent scarcity of available external energy. Neptune's winds reach speeds that defy conventional physical understanding, up to 2,100 kilometers per hour or 1,300 miles per hour, making them the fastest ever recorded on any planet in the solar system, even exceeding the speed of sound on Neptune. These supersonic winds blow mainly in a retrograde direction, opposite to planetary rotation, a phenomenon that further amplifies the mystery of their origin. The energy source of these winds remains one of the great enigmas of planetary meteorology. While terrestrial winds derive from differential solar energy and Jupiter's are powered by the planet's internal heat, Neptune combines both energy sources uniquely, with internal heat dominating despite the presence of a weak solar gradient. Neptune's most famous atmospheric feature was the Great Dark Spot, an Earth-sized storm system observed by the Voyager 2 probe in 1989. This gigantic anticyclonic storm, similar in structure to Jupiter's Great Red Spot, had peripheral winds of 2,400 kilometers per hour and moved westward at 1,200 kilometers per hour relative to surrounding clouds. However, when the Hubble telescope observed Neptune in 1994, the Great Dark Spot had completely disappeared, replaced by a new storm in the northern hemisphere. This behavior highlights the dynamic and transitory nature of Neptunian storms, which form, evolve, and dissipate on much shorter timescales compared to the stable meteorological systems of Jupiter and Saturn. Hubble observations have documented the appearance and disappearance of at least 6 large dark spots over 3 decades, suggesting these systems have typical lifespans of 2 to 6 Earth years. Beyond the great storms, Neptune's atmosphere shows subtle horizontal bands, bright circular clouds that change on hourly timescales, and southern cloud structures that appear linked to seasonal changes. The brightest clouds are composed of methane crystals forming in the upper atmospheric layers, while deeper formations might contain ammonium hydroxide and hydrogen sulfide. This blue giant's magnetic field also presents unique and puzzling characteristics. Like Uranus, it's not aligned with the planetary rotation axis, but is tilted 47 degrees relative to it. The magnetic field center is also offset by 0.55 planetary radii from the planet's geometric center, an even more extreme characteristic than that observed on Uranus. This configuration suggests the magnetic field is generated in intermediate layers of the conductive mantle rather than the deep core, supporting models proposing distributed dynamo mechanisms in these exotic worlds. The internal structure also reveals a complex architecture that clearly distinguishes it from the gas giants of the inner solar system. At the planet's center extends a rocky core composed mainly of silicates, iron, and nickel, with an estimated mass between 0.55 and 1.0 Earth masses, and temperatures that could reach 5,100 degrees Celsius, comparable to the solar surface. This core is surrounded by a massive mantle of hot ices, mainly water, methane, and ammonia in supercritical phase, which constitutes most of the planetary mass. These materials, compressed at enormous pressures and heated by planetary depths, behave like electrically conductive fluids, contributing to the generation of a strong magnetic field. The mantle extends for about 80% of the planetary radius and contains approximately 10 to 15 Earth masses of material. Only Voyager 2 arrived here too. Direct exploration of Neptune, like that of Uranus, remains entrusted exclusively to the Voyager 2 probe, which completed its grand tour of the outer planets with a magnificent flyby of the Neptunian system on August 25, 1989. This encounter represented the culmination of a 12-year mission and marked the final stage of initial exploration of all major planets in the classical solar system. Voyager 2 approached Neptune to within 4,950 kilometers of the cloud tops, the closest distance reached by the probe during all its planetary encounters. During this crucial flyby, the probe transmitted over 9,000 images and collected scientific data that revolutionized our understanding of this remote world. The discovery of the Great Dark Spot, supersonic winds, Triton's geysers, and 6 new moons transformed Neptune from a telescopic point of light into a complex and dynamic world. For the future, several space agencies are developing mission concepts for the ice giants. NASA has identified a mission to the Uranus and Neptune systems as maximum scientific priority for the next decade, while the European Space Agency includes ice giant exploration in its long-term strategic program, Voyage 2050. A unique moon system, the realm of Triton. Neptune's satellite system is distinctly different from those of other giants due to the overwhelming dominance of a single giant moon, Triton. This frozen world, with a diameter of 2,704 kilometers or 1,680 miles, contains over 99.5% of the mass of the entire Neptunian satellite system, an unprecedented mass concentration among the outer planets. Triton orbits Neptune at a distance of 354,800 kilometers in a retrograde direction, completing a revolution in 5.88 Earth days in perfect gravitational synchrony that keeps the same face always turned towards the planet. The retrograde orbit is highly unusual for a moon of such size and strongly suggests that Triton is a captured object, probably a large Kuiper Belt asteroid that was trapped by Neptune's gravity during a close encounter billions of years ago. Triton's surface presents unique characteristics in the solar system, with surface temperatures of minus 235 degrees Celsius or minus 391 degrees Fahrenheit. It's one of the coldest places in the solar system. It shows clear evidence of recent geological activity. Its young surface, with very few impact craters, is dominated by icy plains, rough terrain called cantaloupe terrain for its resemblance to melon rind, and fracture systems indicating active tectonic processes. The most surprising discovery was that of Triton's nitrogen geysers, first observed by Voyager 2. These gas jets reach heights of 8 kilometers above the surface and are carried by winds for over 150 kilometers, depositing dark material in streaks that stain the bright ice. The mechanism powering these geysers remains debated. It could be seasonal heating of nitrogen deposits beneath the surface, or endogenous processes related to tidal heating. Triton's atmosphere, though tenuous, is composed mainly of nitrogen with traces of methane and carbon monoxide. Atmospheric pressure is about 70,000 times weaker than Earth's, but sufficient to support clouds and haze in the ionosphere. This atmosphere is in dynamic equilibrium with surface deposits of frozen nitrogen, which sublimate and recondense following seasonal cycles lasting decades. Neptune's other moons pale in comparison to Triton. Nereid, the second largest moon with a 340-kilometer diameter, follows an extremely eccentric orbit that takes it from 1.4 to 9.6 million kilometers from the planet. This unusual orbit could be the result of gravitational perturbation caused by Triton's capture, which would have disrupted Neptune's original satellite system. The minor inner moons, Nereid, Thalassa, Despina, Galatea, Larissa, and Proteus, are small irregular bodies with diameters between 54 and 420 kilometers that orbit among Neptune's rings. These moons are probably fragments of the original satellite system, destroyed and reformed after Triton's capture. Proteus, the largest of these inner moons, has a distinction of being the largest celestial body that hasn't assumed a spherical shape, remaining notably irregular despite its considerable size. Thin and dynamic rings. Neptune's ring system, discovered in 1984 through stellar occultation observations, comprises 5 main rings named after astronomers involved in the planet's discovery: Gaul, Leverrier, Lassell, Arago, and Adams. These rings are notably different from Saturn's spectacular ones, being extremely dark, thin, and variable in density. The Adams ring, the outermost and most interesting, presents a unique characteristic in the solar system: bright arcs concentrated in specific centers of the ring rather than a uniform distribution of material. These arcs, named Liberté, Égalité, Fraternité, and Courage, maintain their structure thanks to gravitational resonance with the moon Galatea, which confines ring material to specific regions through complex gravitational interactions. Neptune's rings are composed of dark organic particles that reflect only 2 to 3% of incident light, similar in comparison to materials found in C-type asteroids and Kuiper Belt objects. Their age is estimated at hundreds of millions of years, relatively young on geological scales, suggesting they're products of small moon fragmentation caused by meteoritic impacts or orbital instabilities. The variability observed in Neptune's rings, documented by Hubble telescope and Very Large Telescope observations, indicates these systems are dynamic and in continuous evolution. Some ring sectors seem to appear and disappear on yearly timescales, while others show brightness variations that could be linked to seasonal changes in solar illumination. Neptune and the universe of exoplanets. Neptune's importance transcends our solar system's boundaries, extending to the formation of extrasolar planets. Ice giants, as we saw with Uranus, represent the archetypes of a dominant planetary class in the observable universe. Subneptunes, or super-Earths, worlds with intermediate masses between Earth and Neptune that constitute the majority of known exoplanets. Kepler Space Telescope observations have revealed that planets with radii between 1.8 and 4.0 Earth radii are the most common in the galaxy, despite this category being completely absent in our solar system between Earth and Neptune. Many of these exoplanets orbit very close to their parent stars, completing orbits in days or weeks and experiencing extreme environmental conditions that could nonetheless be representative of billions of similar worlds. Neptune's composition and internal structure provide fundamental models for understanding these distant worlds. The transition between planets dominated by rock and metals, like Earth, and those dominated by volatile elements, like Neptune, might occur around 3 to 4 Earth radii, defining a critical frontier in planetary evolution that separates super-Earths from mini-Neptunes. Ice giant formation processes remain debated, with direct implications for understanding exoplanets. If Neptune formed through rocky core accretion followed by volatile capture, this process should be common in other planetary systems too. If instead it formed through direct gravitational instability of the protoplanetary disk, formation times would be much shorter, allowing ice giant formation even in short-duration protoplanetary disks. Neptunian-style exoplanet atmospheres show extraordinary diversity in spectroscopic observations. Some retain dense atmospheres rich in hydrogen and helium, while others seem to have completely lost their primordial gaseous envelope, leaving exposed rocky cores resembling super-Earths. Neptune represents an intermediate case that could help understand atmospheric loss processes and long-term planetary evolution. final reflections, the last frontier. As we conclude this journey through the solar system's frontiers, from scorching Mercury to Neptune's icy depths, we carry with us the awareness that every world visited has contributed a unique chapter to the great story of planetary evolution. Neptune, the last guardian of our classical solar system, greets us from its cold cosmic distances, and its deep blue shines like a distant beacon, keeper of secrets awaiting future generations of space explorers. All right, guys, keep following us for more extraordinary journeys through the mysteries of the cosmos.